So let's take a look at the rocket problem. Or generically, we're talking about I have some object here that is shooting something out the back of it. So the mass of the object is changing, and because this is pushing something out the back, this is being propelled forward. This is what we're working with here. And so let's start out with the basics of the universe. That is the universe. I know that the change in momentum of any system, any closed system, is zero. In other words, you need an external force in order to change the momentum of something. So if this is the universe here, I can then basically make the claim that the total momentum of the universe is some constant. Now, the total momentum of the universe would be just the sum of all the little momentums, I equals 1 to n, assuming I have n objects, would it be equal to a constant? Well, two of the objects involved here are the rocket and what's being projected out the back, and so I have the momentum of the universe is equal to the momentum of what I'm going to call the rocket plus the momentum of the exhaust plus the sum of I equals 1 to n minus 2 of all the other objects. If I look at the change in this, so therefore the in the non-calculus version, this would be delta p, I'm just going to put u for universe, is equal delta change in momentum of the rocket plus the change in momentum of the exhaust plus the sum of the change in the momentum of everything else. For calculus, we'd use dpu. So non-calculus, calculus. For the transition there, if you think of this change as incredibly tiny across the board, so it takes place over very small change in time, then you start getting into this. This is instantaneous, and this is more of a macroscopic view. The change is equal to 0, equals here, with respect to time. And for these, it'd be over delta t. I'm just going to continue on with the calculus notation, but where you see dt, think of that as delta t for the 151 group. So I'm going to bring this over to the other side. So I have dp, the change in the momentum of the rocket with respect to time, plus the change in momentum of the exhaust with respect to time is equal to the negative change in the momentum with respect to time of everything else. And this should just be the external force acting on our system here of rocket and fuel, or whatever is being projected out the back. So this is the net force acting on the rocket and exhaust. In the case of a rocket launch, one of those external forces would be the force of gravity. So if you think about this, there's some external force acting on the system here. Well, by Newton's laws, if there's an external force acting on it, then it must be exerting a force on the external source. And so that's basically what this is right here. This is the force acting on the external source, and the negative of that would be the force, the external force acting on our system. Taking this right here, we have the momentum of the rocket with respect to time equals, I'm just going to subtract that from both sides, so negative change in the momentum of the exhaust with respect to time plus the external force acting on our rocket exhaust system. I know that momentum is mass times velocity, and so I'm just going to plug that in here. So I have the change in mass of rocket times velocity of rocket with respect to time is equal to the negative change in mass of exhaust, velocity of exhaust over change in time plus this external force. Using the product rule, this is mass of rocket times the change in the rocket with respect to time plus velocity of the rocket times the change in the mass of the rocket over change in time is equal to negative mass of exhaust d mass of exhaust dt plus velocity, that should be velocity of exhaust plus velocity of exhaust times change in the mass of the exhaust with respect to time plus this external force. Now recognize if the mass of the object is not changing, then basically what we're left with here is mass times acceleration, mass times acceleration. Now recognize that I have a rocket here that is shooting exhaust out the back. In other words, whatever the gain in mass of the exhaust is has to be matched by the loss in the rocket. In essence, the change in the mass of the rocket with respect to time is the negative change in mass of the exhaust with respect to time. Because whatever one gains, the other one loses. Or if you want to look at it slightly differently, without the calculus version of it, the change in the mass of the rocket must be equal to the negative change in mass of the exhaust, because the exhaust is coming from the rocket itself. When we were looking at this right here, this is just the negative of this. Also, the exhaust. Generally, when we're talking about a rocket problem, what is being shot out the back is small in comparison to the mass of the rocket. And so this right here is a very tiny number. Therefore, this is close enough to 0. This is the negative of that. And so my equation now becomes mass of rocket times dv rocket dt plus velocity of rocket times d mass of rocket dt is equal to, well, I got the negative there and then the negative coming from here. So, or distribute it, and in essence, I have velocity of exhaust times the mass of the rocket with respect to time, plus this external force. If I now have a common thing right here, so I'm going to bring this over. So I have mass of rocket times dv r dt is equal to dmr dt times velocity of exhaust minus velocity of rocket plus this external force. Now let's think about this a little bit here. These velocities are relative to what? Well, they're not relative to each other. They're relative to a third object, like the planet, or there's some reference frame. Whenever you're dealing with velocities, it's always relative to something. So we can explore that a little bit more. I have a rocket here that is cruising at some velocity v sub r with respect to a third object. I'm just going to put G for ground at some generalized reference point. I have exhaust shooting back this way. It has some velocity v sub exhaust with respect to ground. I just didn't write the subscript G before. And so if I have VEG minus VRG, well, that's equal to VEG plus VGR, because this is the velocity of the rocket with respect to the ground, but if we flipped it around from the other point of view, the velocity of the ground with respect to the rocket, in other words, that right there, it's just in the negative direction. So if I have an object moving this way relative to some point on the ground here, if I did it from a different point of view where this object was still, the ground would be going in the other direction. So by flipping around what is the object and what is the reference, we change the sign. If we're just dealing with Galilean relativity, I have the common reference there on the inside, so this just becomes the velocity of the exhaust with respect to the rocket. And so my equation now becomes mass of rocket times dv times in essence, the acceleration of the rocket is equal to the mass of the rocket dt times the velocity of the exhaust with respect to the rocket plus this external force. This right here is thrust. So if we now deal with a special case, if a rocket is out in space, there's no external forces acting on it. In other words, the external force is 0, or close enough to 0 to count, then I basically have a rocket that is being launched. It is shooting exhaust out the back as this goes forward, that the mass of the rocket times its acceleration, again, that's the change in velocity over the change in time, times this acceleration, is equal to the rate at which the exhaust is being shot out the back times the velocity of the exhaust with respect to the rocket. Think about signs. The change in velocity, if this thing is getting faster in the direction it's going in, or if it's getting faster, then the acceleration and the velocity has to be the same direction. Let's just make that positive, just to make life easier. I know that this is a negative number. This is a positive number. Therefore, and mass of rocket is a positive number. Therefore, this, well, fortunately, that is a negative number because the rocket mass is getting smaller. So the change in the mass with respect to time, well, if it's getting smaller, it's got to be negative. And so I have two negatives multiplied together to give me a positive, and that's the way it should be.